So, I will start by showing you a repeat problem which we did in the last class. So, actually this particular problem, while doing it on board, I made a small mistake. So, I will just correct it first. Okay. So, the description of the problem is x equal to 30t minus 2t square, and we have to calculate the average speed between 5 and 6 seconds. So, what we did was we calculated V5, we calculated V6, and by mistake I took the difference of these two. It will be simply the V average will be simply V6 plus V5 divided by 2. If you recall, V5 was 10, this was 10 meters per second, assuming that the distance is given in the units of meters, and this was 6 meters per second. So, your average speed will simply 10 plus 6 by 2 equal to 8 meters per second, not 16 which we did in the last class. By mistake I just subtracted one from the other. Okay, very good. So, with this we will move to our next topic, which is just a minute. Yeah. So, we will discuss motion of systems with variable mass. Now, what is so special about variable mass is, okay, so we have written this equation a number of times, that F is equal to m dv dt, which is correct if the mass of the system is a constant. But assuming that mass of the system is not a constant, this equation in this particular form is not correct. But please note that that does not mean that Newton's second law is not correct. Newton's second law is very correct. Only thing is, if we go by the exact statement of the second law, it says an external force which is proportional to the rate of change of momentum. So, the actual form, true form of Newton's second law is F equal to d dt of mv, not m dv, because m is constant for most of the time. We take it out of the equation, we just write m dv dt. Okay. But when the mass of the system is also changing, we cannot use this equation anymore, but we have to revert back to this equation. Or even better, what we need to do is, in order to get to the equation of motion of a particular system where the mass is changing, we have to slowly and step by step we have to construct the change in momentum at two given time steps. One is time t and one is time t plus delta t, assuming that delta t is small. So, essentially we compute p of t, we compute p of t plus delta t, then we compute dp dt by taking limit delta t goes to 0, p t plus delta t minus p of t divided by delta t. So, this will be our general treatment for system with variable mass. Okay. So, one of the most common system that we study in at the textbook level, where the mass changes as a function of time, is a falling raindrop through stationary cloud. Okay. So, this is one. The second system, which is also very common, that is a balloon rising by dropping sand from it. Third system which we are going to study is the sorry. A conveyor belt. Okay. So, and the fourth and probably the most important system which we are going to study is rocket motion. Now, rocket motion is a rather elaborate treatment, because here the you know we have to first establish the equation of motion, then we have to study the cases with and without gravity in details, and there are many outcome that will so once we solve the equation we will see many interesting things coming out. So, we will keep this for the last. So, in today's class we plan to take these three cases one by one and show you how to construct the equation of motion in each of the cases, and we will take illustrative examples of how to solve each of this type of problem. Okay. So, we will first start with the raindrop through a stationary cloud. Now, what happens here? Let us say this is a cloud which has a mass of capital M. Why I am putting a T here, I will explain in soon. And inside that there is a raindrop which is falling, let us say under the action of gravity. Okay. And the mass of this raindrop is m, which is also a function of time. I will write slightly bigger for your convenience. So, let us say this is also m, which is a function of time. Right. Now, what happens is, as the raindrop falls through this cloud, it absorbs moisture from the cloud and it gains its size and its mass. So, that is why this mass is a function of time. Similarly, because there are mass two body mass conservation laws valid. So, the mass it gains, the mass this cloud will lose. Okay. But once we construct the equations, we will see that in equation only this term will appear or not this term. How? Because this is a stationary cloud. The velocity of this falling raindrop, we can assume that to be v, which is also a function of time, but the velocity of this cloud, because it is a stationary cloud, it is 0. So, this is the situation at time t. Now, what happens at a time t plus delta t? So, you have a velocity which has gone up from v to v plus delta v, a mass which has gone up, mass of the raindrop which has gone up from m to m plus delta m, and the cloud mass has gone down to m minus delta m. So, this is a capital M, this is a small m. Now, if we this is at the time t, this is at a time t plus delta t. So, what are the momentum p and p plus what are the momentum of this system at time t and time t plus delta t? We first have to construct that. So, momentum at this time is m v. Please remember that v is a vector. So, we will just keep writing vector here, okay, plus m into 0, because the cloud is not moving. Okay. Now, for this time point, the net momentum is v plus delta v into again vector m plus delta m, once again m minus delta m, which will be multiplied by 0. So, essentially this is m v plus m delta v plus v delta m plus delta m delta v. So, we try to construct the rate of change of momentum by taking subtracting this from this and dividing the whole thing by delta t and taking this limit. So, this will be dp dt. Please remember that these are vector quantities, okay, dp dt, and we see that immediately this term and this term will cancel out. This term we can neglect because it is a multiplication of two infinitesimally small numbers, okay. It is, so that is why we can ignore this term. So, essentially what we are left with is m delta v delta t. So, just a minute, there will be a limit delta t goes to 0, m delta v delta t plus v delta m delta t. So, if please remember this is equal to F external according to Newton's second law. So, the final equation we get is m dv dt plus v dm dt equal to F external. And if we start from the standard equation without doing all this elaborate procedure, if we simply write Newton's second law in this, in its original form, equal to F external, and take derivative of this, we will essentially get the same equation. So, this and this will essentially give you the same equation, but I will tell you this is this one-to-one correspondence between this. So, basically if I take a time derivative of this, this will essentially be m dv dt plus v dm dt equal to F external, which is identical to this equation. But please do not try to generalize this, because in this particular case it might be there is a one-to-one correspondence between this and that, but we will see very soon that in next few examples this correspondence does not hold. Okay. So, it is better, in order to get to the equation of motion of a system with variable mass, it is always better that we construct this momentum at a time t and momentum at a time t plus del t, and then we take this difference and then divide by t, take this limit, essentially get to this equation. So, this is a much little bit elaborate, but it is rather physically it is rather correct way of getting to the equation of motion. Okay. So, right now we are not focusing on solving it, I will do that when we will be solving the examples, but please remember that we have to put expression for v external, sorry, F external, and also we have to put certain functional form for dm dt. So, we will do that. Okay. But now let us go to the second example which we are going to discuss. So, what we will do is I will just keep this final equation for future reference. Okay. Now, the second equation, second case, that is balloon rising. What happens is a balloon generally goes upwards in through atmosphere because of its buoyance forces. Balloon is basically it is a container, it is a very thin walled container which has lots of light gases inside it, typically helium, and that is why it has a huge buoyance forces that is enough to provide an upward lift to the whole system. So, it can not only the balloon can go up, but it can also carry a certain amount of mass in terms of a gondola, and if somebody is sitting in there. But typically what happens, if as the atmosphere as the balloon goes up in the atmosphere, the air becomes thinner and thinner and the buoyance force decreases. So, at some point the balloon will reach a standstill where the buoyance force and the downwards gravitational force, they are exactly balancing each other. So, the balloon will be stationary. Now, to overcome such situations, we also have, people generally carry a bag of sand in that. Now, typically the bag of sand are extra weight, and it is so what people does is typically they drop the sand. So, essentially the mass reduces, gravitational pull reduces, and the balloon starts moving upwards. Now, it might be very risky to drop a big bag of sand, because it does, sometimes the people who are dropping it, they are not sure where it is going to land. It might land on someone, it might land on some house. So, typically it is done in a smoother way. So, there is a small hole in the they make a small hole in the bag, and the bag loses sand in it loses sand in a slow manner. So, that is why nobody is getting hurt, and also the mass of the balloon reduces and the balloon starts moving upwards slowly. So, let us assume a situation where we have a balloon with initial mass m, which is once again a function of t, and let us say it starts losing sand at a given rate. Okay. So, let us say in time t, the velocity of the balloon is given as v of t, and in a later time t plus delta t, that is at time t. At time t plus delta t, once again we have m minus delta m, because delta m amount of sand has gone down and the velocity is increased from v to v plus delta v. Okay. So, once again we try to construct the momentum p of t and p of t plus delta t. Now, once we do that, we immediately see that the momentum initially was simply mv, and the momentum at time t plus delta t is m minus delta m into v plus delta v plus delta m times v plus delta v. Why this? Why the second term here? Because the sand which get released from the balloon, at the point of release, it also has the exact same velocity of that of balloon. Okay. So, in this case, the mass is released at the same relative speed as the original body. I hope you are getting the point. So, the sand got released from the balloon in a slow manner. As the sand particle releases, the moment when the sand particle releases the balloon body, it has the exact same velocity. Okay. So, that is why essentially if we look into this equation, these two terms cancel out, which leave us with v plus delta v. That is it. So, if we construct dp dt from here, which will be equal to f external according to Newton's second law, what we will get is the difference between these two divided by time, and if we do that, we simply get m dv dt. So, this is our final equation. So, you see, if you start by writing p as mv and take this time derivative, and then you write m dv dt plus v dm dt, you will be fooled. So, this is not right in this particular case. So, if we go back here, so for balloon rising, the equation is simply m dv dt is equal to f external. Now, what is this external force? External force is essentially the fight between upward thrust c and the downward gravitational pull. So, we will do an example of this particular topic, particular problem, and then we will see what are the details of this upward thrust and the downward forces. Okay. But for now, we will just remove everything and we will just keep the final equation. Okay. So, the third topic what we are going to discuss is a topic of conveyor belt. Now, what happens in a conveyor belt? Let us say there is a belt which runs on, we are assuming that it runs on frictionless rollers, and let us assume there is a stationary hopper. A hopper is essentially the stationary hopper. Hopper is essentially the object which is used at different construction sites, which are used for mixing cement and sand together. And let us say this particular hopper is dropping sand on this conveyor belt, which moves along. The sand then, once it get dropped on the conveyor belt, it moves along in this direction with a velocity v of t. Okay. So, now if a amount of sand delta m is dropped in the time interval of delta t, before the net momentum at time t, before the drop took place, the net momentum is nothing but 0. Net momentum, I mean the net momentum in this particular direction, because sand is coming from a direction, sand is dropped from a direction which is the, when it is falling on this conveyor belt, it has a velocity which is in this direction, which is perpendicular to this direction. So, there is no component of velocity in this particular direction. So, the initial momentum is 0, and the final momentum at time t plus delta t is delta m times v of t. Okay. No, sorry, simply v, not v of t, right. So, now we once again construct the equation. So, your dp dt will be limit t goes to 0 delta t times v, which will be simply m v dm dt, which will be f external. So, we see that the equation of a sand falling on conveyor belt and moving along the conveyor belt after falling is f external equal to v times dm dt. So, once again this is very different from this initial equation we wrote here. So, initial equation, it seems like apparently we just started taking derivative of the p term, just writing it as p equal to mv and taking derivative, we got this equation, not like not that. So, we have to follow a step by step construction to get the correct physical insight in order to get to the right equation. So, we write it once again, the final equation for conveyor belt is v dm dt equal to f external. Good. So, we have discussed all these three theory of this behind these three equations, one for falling raindrop, the other one for balloon rising, and third one is for conveyor belt. Now, let us look into the problems. I have collected some of the problems for you. So, first one, let us start with the first one. A raindrop starts falling from rest under the influence of gravity through a stationary cloud. In process, the raindrop gains mass from the cloud at a rate proportional to the product of its instantaneous mass and its instantaneous velocity. The question is, first we have to set up the equation of motion for the raindrop, and then we have to find an expression for the terminal velocity. And that is very nice, because here we do not have any resistive forces, still we could get a terminal velocity. Okay. So, let us try to solve this on board. In order to do that, let us first try to construct the equation of motion. So, we know that for raindrop m dv dt plus v dm dt is equal to f external, and here the f external is mg. Okay. assuming that we are measuring, again once again we have to understand this, we have this stationary cloud, the raindrop is falling with a mass mt and a velocity vt. Okay. Now, where is our origin here? If we place our origin down here, then there is a negative term coming, but let us, for this problem, let us set the origin somewhere up here. We do not care where exactly it is, because we are not planning to give you an exact measure of the distance. We are just trying to construct the equation and get an idea of the terminal velocity. So, we assume that it is up here. So, this g remains positive. So, the final equation if we remove the vector, will simply be m dv dt plus v dm dt equal to mg. Okay. Now, the second information which is given, that dm dt, the rate of change of mass for this particular raindrop, is proportional to instantaneous mass, a product of instantaneous mass and instantaneous velocity, and we can take this as some constant k times m times v. Plug it back into this equation. See, we have to have some model for this mass change. We will take up another example and see if it could be proportional to instantaneous volume, it could be proportional to instantaneous surface area. In this case, it is proportional to instantaneous mass times instantaneous velocity. Unless and until we have a specific model for dm/dt, we cannot solve this type of problems. Okay. So, if we plug this in, we have m dv dt plus k m v square dm dt equal to mg. Simplifying, we have dv dt equal to g minus k v square. So, this is the equation of motion we are looking for, and second part is we have to get to the terminal velocity, and we see that terminal velocity, although there is no resistive force here, because of this mass change is a function of velocity, this itself velocity and mass, yeah. So, this term, it works as if it is an upward force which is working against the gravity. So, in order to get to the terminal velocity, once again we put dv dt equal to 0, we set that, and we immediately get Vt is equal to root g by k. Okay. But here please remember, this k has nothing to do with air resistance, it is a proportionality constant we have used, and we have to have some additional information in order to get this proportionality constant.